Okay, let's continue talking about how very large stars die. And so we've said that these large stars, which are between 8 times and 30 times the mass of our sun, they are going to be able to ignite. They're going to convert hydrogen into helium. They're going to be able to convert the helium into carbon, the carbon into neon, and they're going to be able to manufacture all of these elements up to iron. Then the core is going to collapse. It's going to explode as a supernova. The outer envelope is going to be blown away into outer space, and what's left over is going to be the neutron star. So let's continue by saying what will happen with this titanic release of energy that is going to occur. So normally we say that elements smaller than iron undergo nuclear fusion. So an element that is smaller than iron, when you smash it together, it releases energy. We normally say that elements larger than iron, they release energy when they're pulled apart. So that's nuclear fission. But this thing is going to be, this titanic explosion is going to release so much energy, it will be able to forge all of these elements that were present in the outer envelope, and it's going to be able to smash those together and fuse them into even heavier elements. So elements larger than iron on the periodic table can be fused during supernova explosions. So that's what this chart is for. So the Big Bang, which occurred 12 to 14 billion years ago, made hydrogen and helium. As stars are dying, they can fuse elements from helium up to iron. Okay, then when iron is fused, that creates the supernova event, which can fuse elements larger than iron on the periodic table. Now, there are other ways of manufacturing those elements, and so that is listed in this chart here, but don't worry about it. So I want you to be able to tell me, where did the initial hydrogen and helium come from in the universe? How do the elements, helium through silicon, how are they created? And then how is the element iron created? And then how is the elements larger than iron, how are they fused? Because this explains the origin of the elements in our universe. And so this chart here shows the relative abundance of elements in the universe. Abundance is going up and down, and then the size of the element is going sideways. So the biggest elements are over here, and the smallest elements are over here. Just by looking at the chart, what do you notice? The most abundant element in the universe is hydrogen, followed by helium. That was created at the Big Bang. Okay, but then you should notice that the heavier elements, the amount of them gets smaller and smaller as the element gets larger and larger. Okay, so what does that tell you about supernova events? How often do they occur? Not very often. So notice that the abundance of the heavier elements is smaller because there just isn't that many supernova events that occur. But you notice that the larger elements, the ones from helium up through silicon, you notice that they're more abundant. So that stars do manufacture those elements during the course of their lifetimes, but supernova events are relatively rare. Okay, now we want to talk about a special kind of neutron star called a pulsar. So a pulsar is going to be a rapidly spinning neutron star. So the magnetic field of a star is caused by its rotation. The faster a star is rotating, the greater its magnetic field is going to be. Now, what's happening when a star is, when the star dies and turns from a regular-sized star into a white dwarf, its radius gets smaller. Okay, think about what an ice skater does. An ice skater is going around at a certain speed, and then they bring in their arms. What happens? They speed up. And so that is because of conservation of angular momentum. So if the radius gets smaller, the speed has to get bigger in order to compensate. So as a star turns from a regular-sized star into a white dwarf, radius is going to be getting smaller, so it's going to speed up. So that means its magnetic field is going to get stronger. Okay, now another thing though is the magnetic field axis does not have to align with the spin axis. So if this is a star, and now let's say that the spin axis is straight up and down. So this is going to be an object that is rotating like this. Okay, so you can see the printing going around and around. Okay, so this star is going to be rotating. Okay, it's going to have a magnetic field that doesn't have to be aligned with it. So let's just say, for the sake of argument, its magnetic field is like that. So here's the magnetic field that is tilted with respect to the axis of the star. Now, let's pretend that the Earth is located up here somewhere. So what would that look like? So when the magnetic field is pointing towards the Earth, we would see a flash of light coming from that neutron star. Okay, but then as this thing swings around like this, because it's spinning, so the magnetic field's going to swing around, it's no longer pointing towards the Earth until it swings back around, and now it's pointing towards the Earth again. So what we're going to see is a flash of light, followed by a flash of light, followed by a flash of light. And so it's going to be blinking like this about once every minute or so. Some neutron stars are spinning so fast that it blinks about once every second. Now, when we first saw this, astronomers first saw this, they said that it was aliens trying to communicate with us, because we were seeing these flashes of radio waves. They were pulsing, so we called them pulsars. But then we noticed the conversation was pretty boring. So it was dot, 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 dot. So it wasn't Morse code or anything like that. So then we noticed that over in this part of the night sky, we saw another one. And then over here was another one. So we saw multiple of these things, and each one of them was flashing at a different speed because they were spinning at different rates. So a pulsar is going to be a rapidly spinning neutron star, and what we're seeing, the flash, is energy being emitted by its magnetic field. So I wanted to do a calculation for you here, which you are not responsible for on the exam, but I wanted to know just how fast would different objects rotate, assuming that they all start out being the same size as the sun. So if we assume that the sun is rotating once every 30 days and the sun has a certain diameter, what would happen if our sun was to turn into a white dwarf? So we know the average radius of a white dwarf. So let's say that the radius of a white dwarf is 100 times smaller. Therefore, the speed of rotation would increase by 100 times. And so that's what I did here, was I just estimated the speed at which the sun is rotating and then calculated what would be the new speed of rotation if the diameter shrunk to being a white dwarf. Then I did the same calculation for if it was to shrink to the size of a neutron star. Now, our sun will not do that, but if it did, how fast would it be rotating? And then I did the same thing if it turns into a black hole, which we're going to discuss here in just a moment. So if you want to read that and try to figure out those calculations, then go ahead and do that. Okay, so we've covered large stars, and we have talked about how that they turn into neutron stars. So we're going to take a break, and when we come back, we're going to talk about what happens to very large stars when they die.